Assalamu alaikum everyone. This is Fahd Ansari and I'm here to help you conquer chemistry. In this video we will be looking at a new term, ionization energy. So let's get into it with the definition. Now, looking at this definition, it might seem a mouthful or more to you. So let me explain it with this equation. So in this equation you can see that on the left hand side we have 1 mole of gaseous sodium atoms. Now these are being converted into gaseous sodium ions. Each of these ions has a 1 positive charge, and this was possible when you removed 1 mole of electrons from that 1 mole of gaseous atoms. So the energy change of this reaction is the first ionization energy. We call this first ionization because you are removing the first electron from the atom in order to create the ion for the first time. So energy needs to be absorbed. So it is shown by the positive value of the delta H. Energy needs to be absorbed to remove that first electron from the atom to create the 1 plus ion. So that's your first ionization energy. Now we can continue like this by removing electrons successively one by one. So we pick up from where we left off. We had sodium 1 plus ions over here. That was the product of the first reaction. Now in the second reaction, you are removing 1 more electron from this 1 plus ion, and this gives you now a 2 plus ion. So now that you've removed the second electron from the sodium atom, first you got the sodium 1 plus ion, now you have the sodium 2 plus ion. After removing the second electron, you have the second ionization energy, and you can see energy was once again absorbed in order to do this. You can see this is in kilojoules per mole, kilojoules the unit of energy, and per mole basically means per mole of the ion that has been formed in the gaseous state. So this is the definition of ionization energy. So this was first ionization, and the second equation represents the second ionization. Similarly, if we were to remove another electron, this time from the 2 plus ion, if we were to remove another electron, that would mean we have removed 3 electrons in total, and the product is now a 3 plus ion. So this is going to be your third ionization, and the energy change will be your third ionization energy, or IE. Or you could say this as delta H I 3. 3 for third ionization. So let's look into the factors that affect ionization energy. The first is how far the electron is from the nucleus. So here we have an example. You can see that in the lithium atom, you have your positive nucleus over here, and the first electron that needs to be removed from this atom to give you lithium 1 plus ions is over here. You can see that it is in the second principal quantum shell, or the second shell. All right, not too far away from the nucleus, the positively charged nucleus that is holding on to this electron, whereas the first electron that needs to be removed from the sodium atom in order to give you sodium 1 plus ions is over here. It is not in the second shell, but in the third principal quantum shell. So you can see that this electron is further away from the nucleus in terms of shells, and so the nucleus is not able to hold on to it with a strong grip. So the energy that needs to be gained by this electron in order to escape the clutches of the positive nucleus will be less. And you can see the proof is in the pudding. We have positive 519 for lithium and positive 494, the first ionization energy for sodium. Then the next factor is how many electrons there are in the inner shells. Now, in the lithium atom, you only have these 2 electrons that are coming in between this electron that needs to be removed and the nucleus over here. So these electrons, when they come in the way, they basically um, uh, divert the attention of the positive nucleus away from this electron that needs to be removed. So they basically shield the outer electron from the full attractive effects of the nucleus, so they are known as shielding electrons. So these are known as shielding electrons, and in this case we only have two of them. So the electron that needs to be removed, it will still feel quite a bit of attractive force. Now this electron that needs to be removed has quite a few shielding electrons. So instead of just having two, you have 8 in the second shell and you have 2 in this first shell. So shielding electrons for the sodium atom turns out to be 8 plus 2, that gives you 10. So because you have more shielding electrons coming in the way between the positive nucleus and the electron that needs to be removed, the nucleus cannot focus its efforts on retaining this electron, so it is easier for it to escape. Meaning, in other words, it needs to gain less ionization energy. The third factor is how many protons there are in the nucleus. Now, if the outer electron that needs to be removed is from the same shell and you have the same number of shielding electrons, then you look at this factor. So in the case of boron and carbon, you can see that you only have 2 inner electrons over here and over here. In the case of boron, you have 2 shielding electrons. And you could say the same about the carbon atom, one over here and one over here. And you can see that this outer electron that needs to escape is in the second principal quantum shell in the case of boron, and the same story for carbon, second principal quantum shell. So both of these outer electrons that need to escape are the same distance away from the nucleus in terms of shells. They have the same number of shielding electrons or inner electrons blocking the nucleus from getting a good hold on that electron. So the differentiator is the nuclear charge. In other words, the positive charge of the nucleus or the number of protons in the nucleus. So the nuclear charge for boron is positive 5. That's the number of protons in the nucleus of a boron atom. And for carbon, the nuclear charge, according to its proton number, is positive 6. So positive 5 versus positive 6, which one wins? Obviously, this one for carbon. So the electron, the outer electron of the carbon atom, will have a higher ionization energy. It will need more energy in order to escape. So you could take this as an example. So imagine this is you. You're trying to chase someone in the crowd. Now, if that someone in the crowd is this lady over here, this is an electron that you're chasing. She's pretty close to you, and there are not many people coming in the way, meaning shielding electrons, and she's not very far from you, meaning not many shells away from you, the nucleus. So she will need a lot more energy to escape you. On the other hand, if this lady over here is the electron that you're chasing after, then you can see that there are a lot of people coming in between you, the nucleus, and her, the electron that is looking to escape. There's a lot of shielding electrons in between you guys, and she is many more shells away from you, a greater distance away. And the nuclear charge, basically, it's all on you. If you're strong, then you can hold on. But if you're weak and frail, then you cannot keep up the chase for very long. So in the next video, we will look at how ionization energies work as experimental proof of electronic configurations. And we'll also look at trends of first ionization energies across a period and down a group of the periodic table. If you like this video, do leave a like, subscribe to the channel, and inshallah I'll see you in the next video.